The last activity demonstrated a fundamental difference between types of control that use sensor information and types of control that don't. And so in that activity, I mentioned that we'll use this terminology throughout the course. And this is the distinction between open loop control versus closed loop control. And oftentimes we'll call that feed forward versus feedback. And here, in the open loop case, this means that the input U does not depend on the output Y. And easy example of this that is not exactly much of a dynamical system, but is something that we've all interacted with, is simply a clothes dryer that is on a timer. So here you set it to medium heat and you let it run for 20 minutes. And it doesn't matter if the clothes are really wet or really dry. At the end of the 20 minutes, it's going to stop. And so there's nothing about the sensor. In that case, there's not even a sensor, a moisture sensor, but there's nothing about that sensor that would be fed back. Contrast that with a closed loop system where the output is actually fed back in to the system. And so the example of the clothes dryer, your more modern clothes dryers have some sort of moisture sensor so that when the clothes become dry, it stops the cycle. And so that's a very easy, very simple controller. And the role here of the controller would just be to either continue or to stop. But our job is to be able to design this for much more sophisticated systems and much more complicated control objectives. Building on those very simple block diagrams, we will work with block diagrams a lot in this course. And for the most part, our block diagrams will look something like this. In some cases, they could be simpler. In some cases, they could be a little bit more complex. So we've already seen that our input control signal goes into our system. So our system is indicated by this dashed line. And our system is the combination of actuators and some sort of process dynamics. And it produces the output that we get to see. And the output is sampled by this sensor, and that sensor sends information back to the controller. In this case, it becomes a little bit more complicated. We're explicitly showing that there could be disturbances that could affect the process. There could be sensor noise that affects the value that the sensor is getting back. So you may not get the output back directly, but you may get some slightly perturbed version. And we're also putting in something that we'll talk about very soon, which is this idea of a reference. And in this case, the reference is oftentimes the value that we would like to achieve with the controller. So this could be the speed you choose for your cruise control. Then the controller's job is to achieve that reference, achieve that speed by measuring the current speed and then applying more acceleration if it's required to reach that speed. And so this last box here, this input filter, this could be best thought of right now as essentially a change of units. So in this case, the reference may be specified in miles per hour, but the control signal, if this is a Tesla, maybe the control signal is actually going to be voltage to the actuator, voltage to the motor. And so somewhere in between the reference and the control signal, we need to change units from miles per hour to volts. And so it's possible that that may occur to some extent in this input filter. So another thing that's very important to kind of keep in mind, since this is the first time we're seeing a block diagram, is what the block diagram is telling us. The block diagram encodes signals and transformation of signals. So the wires, these arrows, these wires that move the signal from one box to another, these are where the signal lives. So the reference comes in along this signal. The control signal happens along this bit of wire. And you can think about the blocks then as essentially doing math. they change the signal, they transform this signal, they could multiply it by 2, they could multiply it by 2 and divide by 3, they could multiply it by 2 and subtract 5, they could do all sorts of different kinds of math. The idea is that you've got signals, for example, the output signal coming here, and now the sensor does something. In this case, hopefully it does a pretty good job of measuring the output, but maybe you add in some sensor noise, and so a new signal appears on this edge, and it should be something very, very similar to the output, but it could be slightly different because of, for example, this sensor noise. So the role of these blocks is to do math, and the edges between the blocks are the signals that are communicating different values, and these are things that could be viewed, for example, on an oscilloscope. So that seems maybe pretty obvious right now, but this gets more complicated, and keeping the difference between the blocks being able to do math and the edges essentially encoding signals is really important. And the last bit that I have not described is this, and this is simply a sum. In this case, this signal comes in with a positive sign, and this signal comes in with a minus sign. And so even though this is a sum, it's really a difference. And so we're computing the difference between the reference and our sensor measurement. Now, before we start talking about specific control problems, the last thing at a very high level we want to talk about are our conventional control goals. And so these can be binned largely into 4 different categories. And so we'll be talking about these 4 things. These are the 4 things we want to achieve with our control designs throughout the whole semester. The first one that we often want to achieve is stability. And so this means that a system should effectively be well-behaved. Physically, systems rarely go to infinity. That's more of a theoretical kind of idea. But I think this idea of stability, that they behave nicely, is something that's rather intuitive right now, but we will make that more precise as we move along, what it actually means for a system to be stable. The conventional example of something that is not stable is a microphone that gets too close to its speaker, and you get that really annoying squelch. And so that's an example of a system that is not stable, because there's the sound output that's essentially blowing up and causing that painful sound. Our second control objective is going to be to accomplish tracking, and this is where that reference that we talked about on the last slide comes around. And so this is the idea that we provide some sort of command signal that we'll call a reference, and the output should achieve that as closely as possible. And so we've all used cruise control probably, and so in a cruise control in a car, we all know that if you, for example, go up a hill, all of a sudden you can feel the car doing something different, and that's because it's kind of perceiving the output, no longer tracking the speed that you wanted it to, and now it has to make changes. And so that tracking objective doesn't always have to be a static reference. That reference could be something that changes over time, and so that goal can be kind of arbitrarily complicated. Another important attribute or goal for control design is that we reject disturbances. And this is the idea that if we have some sort of disturbance that's affecting our system, so you can imagine a plane flying and there being a lot of wind, ideally we would like to be able to still maintain our altitude despite the fact that there may be a strong cross breeze. And so we've kind of earmarked that input as this W input, something that we don't always get to design. And so we need to make sure that we're relatively insensitive to that disturbance input. Finally, our last main control objective is robustness. And so this seems a little bit similar to disturbance rejection, but robustness is really the idea that we design all of our controllers with a given model or understanding about our system. So for example, you may design a system knowing that a spring coefficient is some value, but as that system ages, it's possible for that spring constant to essentially change over time. So if you've ridden in a car that has very loose shocks because it's a lot older than a newer car, you kind of experience that, and the fact that the characteristics of the system can change over time, but ideally we'd like our control goals to still be maintained despite the fact that the system may change. Or maybe we didn't model it correctly from the beginning. So we're going to revisit these 4 control objectives over and over throughout the semester. But it's great to keep these in mind as we go through the examples that we're going to see, and then we're going to slowly check these off once we get back to doing control in a couple of weeks.